February 18, 1943. A silver prototype sweeps over Seattle with a wing on fire. The second B-29 has barely left Boeing Field when the flames erupt. Test pilot Edmund "Eddie" Allen fights to bring the bomber home. He doesn't make it. The aircraft strikes the Fry packing plant. In that moment, it isn't a weapon, it's a riddle. How do you make the most complex airplane on Earth work at all? Rewind a few years. In 1939 and 1940, the Army Air Corps asks for a very heavy bomber, long range, high altitude, fast, and heavily armed. Boeing answers with Model 345, the design that becomes the B-29. In a wartime gamble, the government orders the airplane before its first flight. On September 21, 1942, the B-29 finally flies. It promises altitude, range, and payload no one has fielded before. Now, the promise has to survive reality. What makes the B-29 alien in 1942 is not just size. It's an architecture ripped from tomorrow. Pressurized crew compartments, forward and aft, are linked by a narrow tunnel that arches over the bomb bays. Crews can move between stations at 30,000 feet without depressurizing the airplane. It is elegant, practical, and years ahead of its time. Defense goes digital, 1940s style. The General Electric Central Fire Control System puts remote, low-drag gun turrets under the control of gunners looking into periscopic sights. Analog computers correct for ballistics, lead, and parallax, and servos move the guns. A single gunner can command multiple turrets against a threat rushing in at 2 or 10 o'clock. It is the bomber equivalent of a networked air defense node, built from gears and vacuum tubes. And yet, the hardest problem sits in the nacelles, the right R3350. On paper, 18 cylinders and more than 2,000 horsepower are the keys to altitude and speed. In practice, the engines run hot, leak oil, swallow valves, and, if a fire starts, burn through the firewall. Engineers go to work on cowl inlets, cowl flaps, and outlet geometry, hunting for cooling air without killing performance. It's aerodynamics, thermodynamics, and sheer stubbornness, all in one aluminum sleeve. The payoff is real. With improved cooling and mixture control, crews can cruise higher or heavier, trading drag for margin, margin for range, and range for options. That's not a tweak. That's mission geometry changing on a chart. Now put this engineering drama in Kansas, winter, 1944. New B-29s roll straight from 4 factories to open-air modification centers. The Battle of Kansas, veterans call it. Sub-zero wind, floodlights, and rows of brand new bombers waiting for wiring fixes, engine changes, and structural reinforcements. Mechanics and line crews work through snow and darkness to turn prototypes into a fleet. By spring, the airplanes are ready to cross oceans. Why the urgency? Politics and physics. Washington has promised bombers over Japan by spring 1944. Logistics are brutal. Early missions will launch from India and China. Supplies must fly over the Himalayas. Sometimes the B-29s carry their own fuel forward just to enable the next strike. The airplane's problems are being solved while it is already at war. Step back and count what's built into the airframe. Systems integration at a scale completely new to bombers. Pressurization, central fire control, and radar working together. Manufacturing concurrency across multiple factories and field modification centers. Engine cooling advances that turn keep it running into how much can we carry and how high can we go. Mission-specific subvariants, improved wing structures, stripped night raiders, and the silverplate aircraft for special stores. The numbers tell their own story. a wingspan of more than 141 feet, a service ceiling past 33,000 feet, a range measured in the thousands of miles, a typical bomb load that dwarfs what came before. But the real figure that matters is time. In a handful of years, an industry taught itself to build the future at scale. There's a human picture inside those numbers. A flight engineer watching temperatures like a stock ticker, a gunner riding a sight instead of a turret, a navigator building a four-dimensional problem from stars, radio beams, and dead reckoning, a crewman crawling the tunnel while the bomb bays yawn beneath him, and on the ground, mechanics with numb fingers and safety wire in their teeth, turning wrenches in a Kansas crosswind. Legacy arrives quietly. The B-29's architecture, pressurization, centralized fire control, system-level thinking, jumps straight into the post-war bomber force and into civilian airliners. It isn't just that crews fly higher and faster. It's that airplanes become integrated systems. And integrated systems are how the next century will fly. Call it what it was. A systems integration moonshot delivered under fire. The prototype that burned over Seattle becomes a production line that feeds a theater, a maintenance doctrine, and a nightly schedule. Unlike many wonder weapons, the B-29 carries its complexity into repeatable operations, mission after mission. In the end, the B-29 is more than an airplane. It's a rehearsal for the age of complex aerospace. Pressurization made altitude normal. Remote fire control made teamwork electrical. Engine and cooling work turned fragile power into reliable margin. The airplane that barely made it off the runway became the machine that changed how we build, how we fly, and how we think about what a crewed aircraft could be. If you board a pressurized airliner today, if radar, computers, and crew coordination guide your flight through cloud and night, you're living in the future. The B-29 rehearsed. The Superfortress didn't just carry bombs. It carried a new way to make the sky work. Scale becomes its own character. 4 production lines, Boeing in Wichita and Renton, Bell in Marietta, Martin in Omaha, plus a web of subcontractors across the country. Airframes are built, ferried, modified, and dispatched, while procedures evolve on the flight line. Even basic technique changes. On hot, heavy island runways, crews delay the initial climb to build cooling airflow through the cowl. That's engineering turning into habit. The cost is staggering. By the end of the war, the B-29 program has consumed more money than the atomic bomb project. The most expensive American weapons program of World War II is not a laboratory. It's a supply chain with wings. What arrives in the Marianas in late 1944 looks like science fiction. A pressurized, remote-turreted, long-range bomber with a wingspan over 140 feet, cruising above 30,000 feet with a bomb load that shames its predecessors. The specifications aren't just numbers, they're options. High altitude to ride above weather and flak. Long legs to reach targets that used to be safe by geography alone. Systems that let a crew fight the airplane as a team instead of a collection of separate stations. If you could peel back the skin in flight, you'd see how those decisions interlock. Forward, the pilots, bombardier, and navigator